Bismillah wa salatu salam ala Rasulillah. Today we're gonna talk about my project, and it's about 4-bit up and down binary counter using flip-flops. The introduction. Like I bought two important questions, which is what is the binary counter? Second, what are the flip-flops? What is the binary counter? A binary counter is a digital circuit used for counting purposes. For example, BCD binary counter and up and down binary counter. What is the flip-flops? A flip-flop is a basic digital memory circuit used in electronics and digital systems. It can store one bit of information, either 0 or 1. Types of flip-flops, which is D and T and GK flip-flops. Asynchronous up and down counter, T flip-flops, using T flip-flops. It's a type of digital counter that can count in both increasing up and decreasing down order depending on a control input signal. Why we called it asynchronous? It's called asynchronous because all flip-flops within the counter are triggered simultaneously by a common click signal. Applications: digital clocks, frequency dividers, any system where bidirectional counting is required. This is the logic diagram for my project, and the circuit on the right can be used in bidirectional up and down counter with the following configuration options. After analyzing the circuit, we've got two ideas or two main points, which is if up 1 and down 0, the counter counts up, and in the next direction or the opposite direction, if up is equal to 0 and down equals to 1, the counter counts down, and so on. And we've got four flip-flops, which is each flip-flop like equals to 1 bit, and we've got 4-bit binary counter. 4-bit 4-bit up and down binary counter. Why I have to use 4 flip-flops? As I said, because each bit required one flip-flop. Like I wrote this equation, which is gonna help you to understand the whole idea. Number of bit equals number of flip-flops. We are dealing with hexadisplay, so you will see in the simulation letters after counting 9. I mean, like we're like dealing with hexadisplay. As you know, in hexadecimal system, after 9, we like represented the numbers by letters. It's started from 10, which is represented by A, and 11 represented by B, 12 represented by C, and so on. Details for counting up. As you can see here, this is our counter, and there are two inputs, which is up and down, and clock, of course, and this is the current state. The current state, this small note gonna like help you inshallah to understand what's going on. If the current state is 0 0 0 0, which in decimal equals to 0, and the digital constant up, I mean this, equals to 1 and down equals to 0, the state will change to 0 0 1 0 0 0, which in decimal equals to 1. That like help us to understand when up is equal to 1 and down equals to 0, it's gonna like counting up. So in the next state, it's gonna be 1 0 0 0 and decimal equals to 1. Details for counting down, which is the same counter here, and the current state, which is 0 0 0 0, which is equal in decimal 0. The next state, if we count down, it's gonna be 1 1 1 1, and we will gonna change this. We will change this like signals here up we will made it 0 and down we will made it 1, the state will change to 1 1 1 1 and so on. And like in hexadecimal system, the 15 equals to f. So it's really important, guys, to understand we are in loop, which is like counting from 0 to 15 and then come back to 0. Report the aim to design, implement, and analyze a 4 synchronous up and down counter using flip-flop, which can count both incrementally and decrementally based on a control signal and to observe its output behavior through digital display. The objectives, it's to understand the working principles of synchronous counters. 2, it's to design a 4-bit binary counter. Next slides, we will see the simulation step by step and see how it does it work. So this circuit simulation in multisym, and this is our circuit, and this up and down, and I made it to count up, which is starting from 0, and this is the lead bar. It's gonna show us how the binary number look like. So it's 0, and then in the binary number it's equal to 0 0 0 0, and this is our clock, which is connected to the flip-flops, which is T flip-flops, and so on. And here it's counting up, which is 1, and this 1 in binary number, which is 1 0 0 0. So, and so on, until we arrive to A, which is A represented by, or 10 represented by A. So, as I said, it's gonna be in the display, like it's gonna be represented by A. So, there is. So, in the binary number, it's equal to 0 1 0 1, and so on until we arrive to 15, which is equal to F, which is equal to, as you can see here in the lead bar, which is 1 1 1 1. So let's move to the multisym. So here we go. As I said, this is my circuit, and it takes a lot of time, to be honest, and the video like will get longer when I bought the design procedure in the video. So I designed it, and it's really simple, not really hard. So I bought the digital constant up 1 and the down equals to 0, which is gonna count up, and as you can see here, it's 0. We run the simulation, it's gonna be 2 3 4 5 6 7 8 until F, and then came back to 0, F and then 0. If we wanna make it counting down, we will put this 1 to 0 and this 1 to 1. It's gonna be counting down, which is 0 F E D and so on. And this is my circuit. Thank you very much for listening, and I hope you're enjoying this project.